In our lava experiments, very often students who are watching ask the question, well, what happens if we do something different? And when you're asking that question, you're basically posing an experiment. You're creating a hypothesis. You have some idea of what's going to happen if you change, for example, the slope or the temperature or the composition of the lava. In experiments, we commonly vary only one of those factors at a time to see how they change the behavior of the lava individually, or sometimes we see how they interact by changing two of those factors at a time. If we conduct experiments over and over again and we get the same result, we're convinced that we haven't just had some chance occurrence, then we begin to eliminate some of the hypotheses, some of the original ideas we had for how those factors might influence the behavior of the lava. And we begin to come up with what we call a theory. That is a more robust, a more strongly grounded and experimentally verified interaction. The first experiment we're going to do is going to emphasize how important temperature is in determining how lava behaves and what a lava flow looks like after it's poured out. We're going to do two pours side by side here, so it'll be very easy to compare those two. The first pour is going to be at a little bit lower temperature, and we'll determine that temperature using an infrared camera that we have all set up over to the side here. After that pour has been made, and it'll be, maybe 6 feet long, something like that, we're going to tilt the furnace back up, we're going to fire it up again, and heat the lava up, and then pour a really hot lava flow afterwards. And as usual, we've got sculpture students who are all suited out here, like Bob, in protective leather gear and face protection to protect them from the extreme heat. As we'll see during the experiment, you don't want to be any closer than about maybe 10 feet from the lava flow because of the incredible heat. The lava is going to come out at about 1200 degrees centigrade, and the radiating heat is tremendous. So they're taking the protective cover off of the spout. Okay, and here comes the lava. You can see it has a very low viscosity, sort of about the viscosity of maybe cement or oatmeal. When it pours down, you can see some bubbles coming out of it, and it's going to be diverted around the corner here and flow down on one side. This is exactly what you could see in Hawaii or Iceland when lava erupts from fissures. You can see the lava now is just emerging, and it's going to start going down our 10-degree slope. The lava's coming out slowly. You can see a crust forming on top of the lava, and that crust is very, very important in determining how the lava flow is going to behave. A good thing to look at here is right where Allison diverted the lava, a cool sort of dam was built, and the lava is being diverted around the corner now down to the end of the spout. The crust is forming on top of the lava. You can tell the temperature just by looking at it. When it's bright orange, it's about 1100 to 1200 degrees centigrade. When it starts to turn black, it's about 900 to 850 degrees centigrade. So this big blob that you can see down below there has starting to cool on top, but inside it's still molten. And if we were to stab that with a piece of steel or something like that, the lava would burst out. A crust is forming on top, and you can see the entire sort of lava channel that we've got there is sort of inflating. The pressure's built up so much that now it's broken out down at the bottom of the lava flow. And this happens in Pahoehoe lava flows. It's well documented in Hawaii and other places where lava grows by the accretion of individual lobes of lava, one at a time. And as this flows out, it'll cool off. The top will crust over once again. As it cools off, becomes strong. It will start to inflate, and then if there's enough lava pressure, it'll break out once again. This is a fascinating part here. You can see where Allison's grabbing the lava and pulling it. It's really tough and gooey, almost like rubber. when you pull on it. You see Noah's just going to take that big flap of lava and put it over on the concrete where it's out of the way. You can see that even though we've stopped pouring the lava in, the lava is still oozing and moving down slope. As the surface begins to cool, the properties of the lava change and the surface begins to wrinkle and make these beautiful folded forms on the surface. You can see it's where it's being stretched the most, the hot lava is coming to the surface, and as it continues to sort of try to creep down the slope. It's just gravity causing the lava flow to move down the slope. Okay, we're covering the spout up once again here, clamping it on so we can fire it up once again and heat up the lava that's in there so we can do now a higher temperature pour. Okay, we're ready for our second pour here. The lava's been heated up for about another 15 minutes. Our intention here is to do the second pour, divert it over to the near side here, and this would be at a lot higher temperature, significantly higher temperature. We'll find out what that temperature is from the FLIR camera that we have operating here. We monitor the temperature right when the lava pours out, as it's getting ready to do now, and then we like to also know the temperature, especially right when it comes out the end of the spout onto the sand, and then we monitor it as it continues to flow down the slope. So, yeah, I think you can already see that it's a lot lower viscosity than the first pour we did. It's pouring pretty fast down the slope here. It's going to turn the corner, and I'll probably pour most of the contents out. Look at that, beautiful. The skin forming on the outside of the lava. It's coming out on our 10-degree slope here, and you can see all sorts of areas that are being stretched. Pieces of the darker crust, which is probably about 900 degrees C, are being floated along, sort of like rafts on the much hotter interior of the lava flow. Understanding how lava flows work relies on us both understanding the relatively simple, viscous, red-hot part of the interior, but also how that crust on the outside affects the lava flow. You can see that gets stronger as it cools off. It's kind of elastic and stretchy, and that basically controls the shape of the lava flow. I mean, one of our ultimate goals is to look at the shape of the lava flow and that we find out in the field, on the bottom of the ocean, on Mars, for example, and then be able to backtrack to where we are here. Say something about the rate of pouring, how hot it was, the slope, and so forth. You can see beautiful, complicated folding patterns developing in the toe of the lava flow, and it's starting to inflate slightly. The farther up the slope in the trough, it's cool, relatively cool on the outside, but it's hot on the inside and flowing down. You can see down near the end of the spout, it's still flowing at a pretty high rate, and the material on the top is folding and piling up, but it's starting to inflate slightly. Okay, so we're sort of running out of lava. We want to leave some lava on the inside, and we just get this icicle off the top there, lava sickle.
No, you want to put the bottom on either side. Yeah.
Can you see look how hard Noah has to pull that. Look how stretchy it is. Some really interesting things to look at here. Look how when you come down the trough, what was a sort of tube where the lava was flowing underneath a cooled crust, that it's now completely collapsed, and it's leaving a big hole back in there. We're getting a view now at our infrared camera, and that infrared camera shows us the temperature of the lava. It gives at least the surface of the lava. Of course, it's hotter inside, but knowing the surface temperature is really what we need to know in this particular case. You can see that it doesn't look like the regular plain light view that you can see. The temperature is indicated by the color that you see, the hotter colors indicate the higher temperatures. You can see that the lava flow now has dropped down to what is about 600 degrees centigrade on the surface, although we can still see some orange patches in little areas there that are still probably up about 1,000 degrees centigrade. Okay. So this is how we monitor the temperature as the lava is poured. It cools very, very rapidly. We poured it at almost 1,200 degrees centigrade, and now it's already down to about 600 degrees. It's lost 600 degrees already. It actually loses almost 100 degrees just when we pour it from the spout down into the steel trough that directs the lava. It'll take, for this lava that's, maybe 10 centimeters thick, it probably won't really be cooled off until tomorrow sometime. In this series of experiments, we've tried to keep all the parameters more or less constant except temperature, to emphasize just how strongly dependent the lava flow behavior is on temperature. We had a higher temperature on one lava flow than on the other one, so we could compare the behavior of the lava. Now you may notice that the one lava flow, the higher temperature one, actually was a much shorter flow. That's just because we didn't pour out very much lava in that particular experiment. In the longer flow, which was actually the lower temperature, as we watched the lava, we could see that the viscosity and the way it flowed was very different from in that first one. In the experiments that follow, we're going to vary some of those other parameters and see how temperature and those other parameters might be related. We're going to start looking at how the slope affects the shape of the lava flows, and also how the rate of pouring begins to affect the shape of lava flows.